Welcome back everyone, and today we're going to talk about a different type of network security, and that is securing your remote access to resources. That is, how do you connect securely from any remote location? Well, it might be a sunny exotic beach, it might be a hotel or a coffee shop or from a plane perhaps. It's all about securing the type of communication because it's supposed to give you access to resources that you normally would have access to if you were in your office or at home. Now, those remote access connections, if you still remember those a while ago, were performed by using a dial-up modem or a leased line. Nowadays, we don't really have the luxury of having a dedicated network or a dedicated connection just for the purpose of remotely accessing resources. But what we're doing nowadays is to run VPN connections, virtual private network connections, directly over the internet, because everyone has access to the internet. So why not use it to gain access to your home or work resources as well, of course, in a secure manner. Now, of course, with great flexibility comes great administrative effort. That is because whenever we're starting to allow remote connections from anywhere or any type of device, from an administrative perspective, this becomes a lot more stuff to secure. So for example, just think about the fact that people now can connect from their mobile devices, and those mobile devices can be virtually anywhere, even outside of the country's borders. We also have to take into account the diversity of the devices that user will be using to connect. Some of them might be using Windows operating systems. Some of them might be using Linux operating systems. Some of them might be using legacy mobile devices that have been out of support for many years, such as, I don't know, Blackberries, for example. You also have to take into consideration that whenever you're allowing remote access connections, you are no longer in control over the network that is being used by the client that is supposed to connect to your VPN endpoint. The client might be using a completely insecure network. It might be a public Wi-Fi in a hotel or an airport or a coffee shop. They might be at home. They might be in some competitors' building, perhaps. So you lose control over the network that is being used to access your resources. So the root of all remote access connections is going to be generically called a VPN, virtual private network. It's just a logical tunnel, logical connection that is being constructed between you, your remote client, and the head end or the data center or the parent device that is located at the end of the VPN connection. So what exactly are you connecting to? What is the server, the VPN concentrator, the VPN endpoint that you're connecting to? Well, that's the other end of the tunnel. It's usually encrypted. It's funny because everybody assumes nowadays that whenever you're talking about VPNs, you're talking about security. It's encrypted, it's authenticated, it has integrity built into it. Everything is taken for granted. Unfortunately, the term virtual private network doesn't assume encryption anywhere. The term virtual private network simply means that you're creating a private network between you and the company, which is created just for you. That's the tunnel. And it's virtual because it's defined in software. Nowhere in this definition is anything mentioned about security. So it's not just a theory, this, but by default, the VPN technologies actually don't implement security. You need some additional functionality on top of that VPN technology to make sure your data is secure. So it might be just a small interesting trivia for you, but keep this in mind for exam as well. VPNs are not by definition secure. They can be, but it's not a mandatory part. Now, one important term here, actually two important terms that you need to become familiar with are remote access VPNs. Those are the VPN connections that are being initiated from your own machine, from a VPN client running on your own machine. Maybe the native Windows or Mac OS VPN client, maybe you have some third party such as a Checkpoint VPN client, maybe a Forti client, whatever you have on your machine, that's going to be a remote access VPN. Now, on the other hand, we also have something called a site-to-site VPN. That is a more permanent type of a secure connection of a VPN. Now, in many situations, the protocols and the algorithms used in both the remote access and site-to-site VPN are going to be pretty much the same. But a site-to-site VPN is designed, just like the name says, to protect the connection between two sites, between two networks. So for example, you might have a company headquarters in a city, you might have 10 branches all over the country. Those branches are expected to have a 24/7 non-stop secure connection to the head end office. Well, that connection, that non-stop connection, is also going to be a VPN, but it's a different kind of VPN. It's set up in a different way, and it's called a site-to-site VPN. One major difference between remote access and site-to-site VPN connections is that while remote access VPN is designed to give you access as a single user, a site-to-site VPN is designed to give access to a whole bunch of users, to a whole bunch of resources. So all the users that are located in a specific branch office, they're all going to be using transparently and completely unaware the same VPN connection in order to reach the resources at the headquarters. It's usually established using two dedicated devices, like two routers, two VPN concentrators. It might be maybe just two virtual machines perhaps. But in many situations, we're using two firewalls with advanced functionality such as a next generation firewall or a UTM device that is able to initiate both site-to-site and remote access VPN connections. Now, the most common type of remote access connection nowadays is called a TLS VPN, more often found under the name of SSL VPN, simply because people have gotten so used to the SSL terminology. But officially, what's running inside of it, it's now TLS. So it's kind of a connection that is very similar to what we're seeing whenever we're connecting over HTTPS to a website, to a secure website, right? So we have a server that has a certificate. We're connecting to that server. We're validating the identity presented in that certificate. If we're able to validate the certificate, or if we're able to validate the digital signature in it, then we accept the fact that the identity is correct and we continue communicating with that server in a secure manner. Well, optionally, of course, the server can authenticate the client because it becomes a bit more important to validate the identity of the client whenever we're establishing a VPN session. So the client would be invited to present a username and a password, perhaps a certificate, perhaps a smart card, perhaps maybe multiple factor authentication, right? The username and the password and biometrics, for example. Since we're running over TLS, and it behaves really similar to HTTPS, it's also going to be initiated on port 443. Now, of course, just like with any other ports out there, I know I'm repeating myself when I'm saying this, but ports are just a convention. It's just for people and applications to expect to receive a specific type of traffic on a specific port, but nobody's stopping you from reconfiguring your VPN concentrator, your firewall to listen for TLS VPN connections on a completely different port. And by the way, you can also run it over UDP. And you might think, wow, why UDP? I mean, everybody hates UDP, right? It's unreliable, doesn't have any acknowledgements. And the good news is that networks nowadays are pretty reliable. So we're starting to see UDP protocols more and more, simply because we don't really need every single time the overhead of TCP. So we could be running a completely encrypted TLS connection or a TLS VPN over UDP with much less overhead. Now, if it's running over UDP, it's called DTLS. You probably guessed it. It's called Datagram TLS, right? Datagram being the official name of the UDP payload. Also remember that in enterprise environments, most likely there's going to be an authentication server involved in there as well, or a AAA server. It might be Radius, it might be TACACS, but it's some sort of a centralized database of user credentials and user identities that is being used every single time a user tries to connect to the network, be it locally over 802.1x, for example, or over the VPN connection. They still have to present the same credentials, they still have to authenticate themselves, and that authentication information needs to be passed over to the AAA server and validated on that server's database. Some implementations of TLS VPN out there that you might have heard about are Cisco AnyConnect's implementation, which can, by the way, use both IPsec and TLS. In most cases nowadays, it's using TLS. OpenVPN is also an implementation of TLS VPN, and Microsoft SSTP, which stands for Secure Sockets Tunneling Protocol. For some reason, they felt the need to give it a different name. Microsoft SSTP is another implementation of a TLS VPN. And yes, the last bullet on the slide right here, TLS VPN works at the application layer, which is probably not surprising since it's an application layer protocol. We said that the communication is very similar to HTTPS, right? HTTPS also runs at the application layer. This is relevant because while we have this VPN technology that runs at the application layer, here comes one that doesn't run at the application layer. And that one is called IPsec. It's an entire suite of protocols or algorithms and key exchange methods and whatnot. We're going to see more about them in just a minute. What's important about IPsec, at least at this level, is the fact that it doesn't run at the application layer, it runs at the network layer, on top of the network layer itself, at layer 3, which means that it can be implemented at the network layer without involving the application, without having to change the design of the application that is sending data over the IPsec tunnel, which from one perspective is an advantage because you don't need to change your applications. From another perspective, it's going to be a pain to administer because it requires you to redesign and reconfigure your actual networking devices. So it's tunneling at the network layer, and it can encrypt and or ensure integrity of all the network packets that are traveling over it. It has no application awareness, so it really doesn't care what goes on within that IPsec tunnel. It simply encrypts and signs everything blindly. Well, at least as long as a valid IPsec tunnel has been previously established. Now, a disadvantage of IPsec is the fact that it adds quite a bit of overhead to your communication. And if you think about it, simply because it runs at the network layer, it means it's going to add some overhead to each and every of your IP packets. So if you can live with this, IPsec might be a good solution for you. Now, this overhead happens with IPv4 a bit more than it happens with IPv6 because IPsec is now built into IPv6. So the functionality is already there. You don't need any new headers. It's already there. You just need to enable it at a network layer in order to be able to use IPsec over IPv6. Now, the configuration of IPsec is actually a configuration of a set of policies. And a policy is nothing more than a collection of connection method, authentication algorithms, encryption algorithms, key exchange algorithms, whatever we need to prepare in order to establish a secure connection between two endpoints. And as part of that security policy, we can use two protocols. We can use them separately or we can use them together. These protocols are authentication header, also known as AH. It's just like the name says, a method for ensuring authentication for your IPsec packets. Now, authentication means that we're ensuring that the packets are coming from the right entity and also that the packets have integrity, that they haven't been tampered with. There's nothing here to protect the packets against eavesdropping. There's no encryption here, right? Just like we said before, if you think about VPNs, if you think about IPsec, everybody's going to think that, well, you're working with encrypted data. Well, it's not the case. It's not always the case. AH is a type of protocol that if it's implemented standalone by itself, it doesn't ensure any type of confidentiality. But it does ensure integrity by hashing the data and combining that hash with a shared secret, right? Because this is how you validate identity. And by combining the hashing with a shared secret, this is how you're generating an HMAC value that is added to the IPsec packet. And the field inside of the IPsec packet is called the ICV field, the integrity check value field. And kind of looks like this. So whenever you're adding the AH header inside of your IP packet, notice that it actually falls between the IP header and the TCP header, right? Now, whatever follows the AH header, starting with the TCP header, is going to be authenticated, which means that whenever somebody tries to tamper with our data, the AH header is not going to be valid anymore, and the intrusion is going to be detected. But that's all it does. It doesn't encrypt the data. Now, AH is being announced in the IP protocol number as number 51. Now we need this because normally, if you come back to this diagram right here, normally the IP header here on the left would announce in its protocol number that there's a TCP header or a UDP header coming up right next in the series of encapsulations. Now, since we have a new header in here, we need to announce it inside of the IP header. So instead of announcing in the IPv4 header something traditional that's coming up, such as number 6 for TCP or 17 for UDP, we're going to announce something that's located right here under number 51, that is authentication header, right? AH. That applies to IPv4. If you're talking about IPv6, that's going to be a separate extension header. Kind of like optional headers in IPv4, we call them extension headers in IPv6. We have an extension header for AH. And as I said before, it ensures no confidentiality whatsoever, and it can present a couple of issues with some protocols. The first type of issue might be with protocols that dynamically change port numbers. And it can present a big issue depending on your network design. And that big issue is if your network uses NAT. So why is NAT a problem? Now, coming back here to this initial diagram, if you think about NAT, well, network address translation, it leads you to think that only the IP header gets changed. But remember, if you're doing a NAT overload, if you're doing port address translation, you might not just be changing the IP header of your packets, but you might be also changing the TCP or UDP port numbers. Well, unfortunately, this TCP area right here kind of becomes off limits because it is now being authenticated by the AH header. So if a hash is being calculated with the initial values in the TCP header, and then some NAT device along the way changes some ports in the TCP header as a part of the normal NAT process, well, that packet is going to fail authentication. It's going to fail its AH validation because it's not going to be considered a valid packet anymore. And of course, we do have ESP, encapsulating security payload, which finally is about encryption. So we're finally talking about VPNs the way you should be talking about VPNs, in a completely secure manner. So with ESP, we can encrypt and authenticate packets as well. Now, it adds 3 elements to the IP packet. That's a header, the trailer, and the integrity check value. So it's a bit more overhead than with AH. In the IPv4 protocol number is going to be announced as a separate header, that is protocol number 50. So we have 51 for AH and 50 for ESP, pretty easy to remember. And again, for IPv6, this is going to be implemented as a separate extension header. Now, another important topic here is the fact that IPsec can be used in 2 modes. We're not talking here about different protocols, but 2 modes of implementing those 2 protocols. First mode is called transport mode. Now, transport mode is designed to be used between hosts on the same private network. So if you don't go out over the internet, or if you're not traversing other networks, you're going to be safe by using transport mode. Now, with transport mode, just like the name says, what we're doing here, if you're looking at the first part of the picture at the bottom right here, is the fact that the original IP header is left untouched. So we have the original IP, we're adding the ESP and or the AH headers in there, we're protecting whatever follows the original IP header, but we're not touching the original IP header. Now, we could touch it in some way by enabling AH. The original IP header is going to get hashed, but it's not going to be part of the encryption process. So we're not encrypting the IP header, because if we're hiding the IP header by encrypting it, there's no way for us to determine how to reach the destination anymore. On the other hand, if you're about to traverse multiple networks, you might be better off using IPsec tunnel mode. IPsec tunnel mode adds another IP header. It's a way of saying, well, I'm going to just apply ESP and AH, whatever combination I want to apply in there, to the entire packet. I want to protect it entirely. So that's why I'm adding a brand new IP header at the outer edge of the packet, so that the new IP header is the one that is going to be used for actual packet routing. Kind of like an IP in IP tunnel. One thing to note here is that AH doesn't make much sense in tunnel mode, simply because AH doesn't change the original IP header. So if you're not changing it, there's no reason to add another one, all right? If you're not losing the original one, why waste MTU space and why waste networking bandwidth by adding an additional IP header when it's completely identical to the original one? Now, we kept talking about encryption and authentication in IPsec, but all of this has to happen based on some secret keys or some shared keys in there. Now, those keys have to be known by both ends of the VPN tunnel, of course, because otherwise I won't be able to validate what you're sending to me, and you cannot be sure that whatever's coming from me is valid. So we need some sort of a mechanism, we need some sort of a protocol to ensure this process for generating keys and for exchanging keys as part of a secure VPN communication, or IPsec. So for this, we have the IKE protocol, the Internet Key Exchange Protocol, which takes care of securing these key exchanges. And these key exchanges are actually called, within the IKE configuration process, they're called security associations, or SAs. In the IKE process is run over two phases. Now in the first phase, we're going to be checking the identities. We're going to be validating either the pre-shared keys that the endpoints are presenting, or we're going to be validating their digital certificates, depending on the implementation. And then we're going to be securing the actual tunnel. We're going to be creating the secure tunnel. Now, as part of the tunnel creation itself, we're going to be generating some random keys that we're going to be using to secure the data. We're going to be using them for encryption and an integrity validation. Now, these keys are generated and then exchanged between the two parties using the Diffie-Hellman algorithm. Next, on to phase 2, we're using the already established secure tunnel from phase 1, this time to negotiate our abilities. Each end of the tunnel is going to present its own supported algorithms, modes, key lengths, whether they support AH or ESP or both or neither, and they're going to be compared in order to select the best combination of the available ones. Now, what we just covered is about IKE, the IKE protocol, and that is IKE version 1, which is mostly designed to perform mutual authentication between two peers, such as in site-to-site VPN, for example, but it's not exactly designed to provide user identity information or authentication to a user in a network directory, such as Active Directory. So in real-life implementations, normally IPsec is combined with L2TP in order to provide remote access, VPN authentication, and VPN connections. So in the combination of IPsec with Layer 2 tunneling protocol, the tunnel that protects the exchange is still IPsec, but the user has the ability now to provide authentication credentials using either EAP or CHAP. Now, an alternative to this combination of protocols is to use IKE version 2, which is an upgrade to the original IKE protocol, better designed for remote access VPNs. It also allows you to choose any EAP-supported authentication method, so you're not just restricted to a pre-shared key, but you can use digital certificates, you can use biometrics, you can use username and passwords, you can use multi-factor authentication, whatever you have at your disposal and whatever is supported by the VPN concentrator. It also supports a shorter connection handshake, less messages, fewer messages, so less overhead. And it also works better over NAT connections. Not just over NAT connections, but also works better for devices that have multiple network connections, such as a laptop that has both a wired and a wireless connection, or perhaps even a 4G or 5G cellular connection. In this situation, IKE version 2 can initiate the connection on one network interface and then keep the IPsec connection alive and going, even if the client changes network interfaces or moves from one physical network interface to another one. Configuring a remote access VPN setup, it's going to require you to interact mostly with the VPN concentrator or the firewall or the UTM device that accepts the VPN connections. That's the largest chunk of your configuration. Now, there are specific settings that can be enabled on the VPN clients as well. Those are the clients that might be the native operating system clients that are available in Windows and Linux and Mac OS, or it might be third-party clients provided to you by the security vendor of your choosing. Nevertheless, even some of these settings might actually get automatically pushed from the VPN concentrator down to your client, and you might not have any say in this. But depending on how the policy was configured, you might get to select one of these possible VPN implementations, such as Always On VPN, which requires your computer to connect to the VPN the first thing it does whenever it detects a trusted or secure network. So it's not going to be able to generate any type of network traffic. It's not going to connect to any destination unless the VPN has already been established. A key differentiator here is the fact that the always-on VPN is most likely going to be initiated by the operating system or by the VPN client itself based on some cached credentials, so it doesn't require any user interaction. Now, on the other hand, we also have two additional options here that are frequently mutually exclusive, and those are split tunnel and full tunnel. Now, with split tunnel, this means that we're going to be using the encrypted tunnel to send our packets only for those destinations that are only accessible over the VPN. For the rest of the traffic, so if you just want to connect to publicly available resources over the internet, just accessing websites perhaps, that type of traffic is not going to go over the encrypted connection. So it's not going to be backhauled back to the headquarters or your VPN concentrator to be forwarded to the internet. No, it's just going to be sent directly over the internet without using the VPN at all. And of course, you can probably guess what full tunnel means. Well, full tunnel, it means that all the destinations, those accessible only through the VPN, and all the other destinations are all going to be sent over the VPN. Now, this type of implementation is usually configured in for a security purpose where all the company hardware or the company laptops or mobile devices, all the traffic that they're generating, we need to be able to analyze it and we need to be able to filter it and apply some policies to it. So we're not going to let our employees, regardless of where they are located in the world, to send their traffic directly to the internet, but we're going to make them, as long as the VPN is enabled at least, we're going to make them send all that traffic to the headquarters, to the VPN concentrator, to be analyzed, to be scanned, to be submitted to specific security policies, maybe URL filtering, maybe reputation filtering, and then we're going to forward that traffic if we consider it to be legitimate to its real destination. Just to mention here some other remote access methods here. You've probably heard about this one. That's remote desktop protocol, just a visual remote connection for graphical user interfaces. You can use it natively on Windows. There are also additional implementations that behave quite similar to RDP. Some of them are dedicated just for a specific application. Some of them are specific to generic operating systems, which allow you complete access to the entire desktop. You might have heard about things like TeamViewer or VNC or even Guacamole, which is a very interesting solution that uses the canvas in HTML5 in your browser to draw the results of a remote connection. It could be a remote text connection, such as SSH. It can be an RDP connection, but the important thing is that you don't really need a dedicated client for it. A simple browser is more than enough. Still on the remote access side, having a dedicated management network just to ensure that you can always access and manage your networking devices or perhaps your servers in your own enterprise network, that can also be considered a remote access method. Now, having a management network remotely accessible from the outside world, from the internet, is probably not a good idea, but it's as long as you're inside of the network, as long as you have access to that management network, that is also a method for managing devices remotely. And by the way, if you're talking about out-of-band management, it could be just a separate Ethernet network, but it can also be a completely separate type of connection, such as a serial connection through a serial concentrator, a serial connection to the consoles of your networking devices that you're planning to manage. And finally, another often found implementation of a remote access solution is by using a dedicated host located somewhere in the DMZ area of the network that you're planning to access, which has the only purpose of concentrating connections from the outside, validating their identities, validating the actions that users are performing in there, and then allowing them access further deeper into the network, perhaps to manage additional devices or virtual machines in there. This type of deployment based on a jump server or a jump box, or sometimes called a bastion host, especially in cloud environments, is often used to protect entire network segments, sometimes even entire separate infrastructures that might be physical or might be virtual or even might be located in some cloud. You're going to find a lot of implementations out there where an entire cloud infrastructure is, of course, not accessible from the outside, but what is accessible from the outside is just a simple virtual machine, which should be, of course, a very hardened virtual machine with a pretty secure operating system. And that virtual machine accepts connections from the outside. Now, once you're logged into that virtual machine, you can reach over SSH, over RDP, over Guacamole, over whatever protocol you have in there. You can reach the rest of the infrastructure. And let's not forget about SSH, Secure Shell, the most common method of gaining access to a command line terminal. It's available on all operating systems. You might be surprised to see that you now have an SSH command even within Windows, but it has been traditionally the de facto method for remote access on Linux. Now, the way SSH works is that the server is identified by its host key, so it does hold a public and private key pair, of which the public key is being presented to you in order to validate its identity, and the client can be authenticated using a number of methods. It can be just a simple password, it can be also a public-private key pair, right? And just in case you want to authenticate in a passwordless manner. So SSH allows you to upload your public key to the SSH server so that the SSH server is going to recognize you and thus allow you to connect without even providing a password. Or you can even use a third-party authentication mechanism such as Kerberos. Some additional SSH tools that might be worth remembering for the exam is the actual SSH command. We also have SSH keygen, which helps us generate the public-private RSA key pair, right? If we want to perform public key authentication. SSH copy ID is a small utility designed to upload your public key to the SSH server so that from now on you can authenticate without any passwords to that SSH server. And SCP, it's secure copy, is basically an implementation of the SSH protocol designed to transport binary information. In other words, it's a way to secure copy files back and forth between your client and the SSH server. Alright, so that's it for today. I hope it wasn't really complicated, apart from that AH and ESP discussion about IPsec. But nevertheless, I hope I've managed to make it interesting and intelligible. So, like, subscribe, support, and see you on the next video. Thank you.